Hey everyone, it's Mrs. Hoekstra here. So since we're not having class again, I'm going to send this off to you guys electronically, and hopefully you guys will be okay between my lesson and what we have going on in the book. So here we go. Let's see here, probability, chapter 9. So today you guys should be able to figure out how probabilities are determined, understand experimental or empirical probabilities versus theoretical probabilities, properties, mutually exclusive and non-mutually exclusive events, and then geometric probabilities. All right, those are our outcomes. All right, so some vocab. Experiment, an activity whose results can be observed or recorded. Think about it honestly, kind of like being in a science class. You're doing an experiment, you can see it. Outcome are all the possible results of that experiment, right? So if you're talking about tossing a die, right? All the possible results out of the outcome of rolling a die, right? You could get 1, you could get a 2, you could get a 3, you could get a 4, you could get a 5, or get a 6, right? All the possible outcomes. Sample space is the set of all of those. So you would just write them out. 1, 2, 3, 4, 5, and 6. Okay, and then the event is any subset inside that. So you could be like, hey, I want to know what's the probability of tossing a die and getting an even, right? So if we talk about evens, then the subset of evens would be 2, 4, and 6, right? And so on and so forth. Okay? So suppose an experiment consists of drawing one slip of paper from a jar containing 12 slips of paper, each with a different month on for the year, right? Find each of the following. So our sample space would be January, February, March, all of them listed out, right? That's your sample space because you're going to list them all out. Then what's the event A, we're going to call it, consisting of the month beginning with J. So you would just list out month A, all of them with J. Event B, all of them that have exactly 4 letters. Well, it's only June and July. Okay, so just pay attention to what your sample is and then just base everything out of that sample. And then, of course, we have any of the months that begin with M or N, so March, May, November. Okay, so once you know what your sample is, that's where you're going to draw all of your choices out of. Okay, experimental probability. This is determined by observing the outcomes of the experiments. This is like you actually doing it, right? You actually do these. So we're talking about really rolling dice, right? Or drawing cards, right? Drawing cards from a deck. Drawing a card from a deck. Versus theoretical probability, this is what we're expecting, okay? This is what we expect to have happen. How many times will you get heads? We expect to get heads on a tails, heads and tails, right? You expect to get heads 1/2 of the time. But if you've ever actually done the experiment where you're like, okay, I'll toss a coin 10 times, do you really get exactly 5 heads and exactly 5 tails? No, that's experimental. That's what really happens. Theoretical is what we expect to have happen. We expect heads half time and we expect tails the other half. But it doesn't always work out that way. Now, equally likely, my students, at least in the middle school, they always get this confused. Equally likely means they all have the same number of chances of being an outcome, okay? When one outcome is equally likely as another. So think of it as, and most everybody thinks, at least in middle school, my middle schoolers think it's 1/2. No, like think about a die, okay? If you have a die, each number has 1/6 of a chance of being rolled, right? So each one has 1/6 of a chance. A uniform sample space means that they all, again, are equally likely. So it's going back to maybe using that die. 1, 2, 3, 4, 5, and 6 all have an equally likely chance of happening. The law of large numbers. As the number of trials of an experiment increases, the experimental probability gets closer and closer to the theoretical. The experimental, right, approaches the theoretical probability. Once, way back when I was working on my master's degree, we were asked to roll toss a coin 1,000 times. Can you imagine doing this? So really what we had was a computer that did it for us. And we had to keep track of it. And sure enough, as you got closer, as we got closer and more into the thousands, we got closer and closer to the theoretical. Okay? So tossing a coin 10 times, the kid's going to be like, oh, it was 6 and 4. Right? Even though we're expecting 5 and 5. And then you do it again and you're like, oh, wow, yeah, we've done it 100 times. And sure enough, we're like at 49 and 51 or whatever. It gets closer and closer to that. Okay. So that's, so really what this is ultimately telling you is you want to have more trials, right? More trials means more accuracy. Okay. If I can spell right. There we go. So probability is the number of elements out of the number of the elements of the subset, right? This is the subset out of the whole sample. Okay. So if I'm trying to figure out what's the probability, let's do an example here of talking about, let's talk about dice, a die, right? So we're talking about 1 through 6. Oop, if I can write correctly, 1 through 6. So we're talking about numbers 1 through 6, and I say, hey, what's the probability of getting a 2? Right? Well, how many times does 2 actually appear? 2 only appears 1 time out of the 6. Or if I said, what's the probability of getting an odd? Right? Well, how many odds are there? Right? There's 3 of them. 3 out of the 6, or 1/2 of the time you will get an odd. Okay? So that's how we're going to figure out probability of equally likely outcomes. So take a look at this one. Let S, that's our sample set, be the numbers 1 through 25. If a number is chosen at random, that is, with the same chance of being drawn as any of the others, calculate each of the following probabilities. Okay? Event A, that an even number is drawn. So we're talking about what is the probability of getting 2, 4, 6, 8, 10, right? So on and so forth. Well, there are 12 of them, right? Well, how many are in the set? How many are in the set? We have 25. So if I had to figure this out without looking on the next page, what's the probability of A, P of A? I'm going to have 12 out of 25. Let's see if I guessed that right. Oh, don't have the answers. I'm going to say I guessed that right. What's the probability of a number less than 10 and greater than 20? Okay, so what's the probability of having a number less than 10 and greater than 20? That is not possible, right? So this is a null or empty set because it cannot be both less than 10 and greater than 20 at the same time. So the answer is going to be an empty set over 25, which is the same as 0. Okay, and the event C, that a number less than 26 is drawn. What is the probability of C happening, right? A number less than 26. Well, how many is that? There's 25 out of 25. That's a 100% chance of that happening, right? Every single number in that set is that way. What's the probability of us getting a prime? Well, there's your primes. How many are there? There's 9. How many are in the whole sample? 25. And what's the probability that we get an even and a prime? Well, how many evens are there in there? Just the 2. The probability of event E happening for us is going to be 1 out of the 25. I've kind of jumped ahead in my notes here, but I think you guys can handle it. Impossible event is an event with no outcomes, right? Not going to happen. Versus a certain event, probability is 1. So probability of 0, never going to happen. Let's see. The probability of me going to Mars, right? Never going to happen. I'm never going to go to Mars. I don't have the degree, I don't have the ability to get there, don't have the money, whatever. Probability of something that's going to be certain, maybe the sun coming up, right? The probability of a sunrise. I know tomorrow the sun will come up. Now, granted, it may be foggy, it may be rainy that day, but the sun does actually rise, right? I know it's a guarantee, 100% chance that that's going to happen. All right. Probability theorems. So probabilities are always going to be some kind of an answer between 0 and 1. It's always going to be either a fraction or a decimal. If A is any event and S is the sample space, then the probability of A is going to be between 0 and 1, somewhere between impossible and certain, right? Somewhere in between, and it's going to be written as some kind of a fraction or decimal. I like fractions, so usually you're going to see me write it as a fraction. If we draw a card at random from an ordinary deck of playing cards, what's the probability that A, the card is an ace? Well, first of all, you have to remember that there are 52 cards in the deck and 4 of them are aces, right? So if I said, what's the probability of getting an ace? Well, there's 4 out of the 52 in the deck. Now, can I reduce that? Yes, I can. I can reduce that. 4 goes into itself once. 4 goes into 52 13 times. So I can reduce that, and I get 1/13. If we draw a card at random from an ordinary deck of playing cards, what's the probability that the card is an ace or a queen? Okay? Or means it can be one or the other. It doesn't have to be both. I have 4 aces and I have 4 queens for a total of 8 cards. Now I'm going to have a possibility of drawing out 8 cards. So what is the probability of an ace or a queen, right? There are 8 out of 52 possible. Again, does that reduce? Yes, it does. 4 goes into 8 2 times, and 4 goes into 52 13 times. Okay, just doubled my chances. All right, let's take a look at a spinner. Since you guys are going to be teaching elementary school, you're going to see a lot of spinners. Events A and B are mutually exclusive if they have no elements in common, right? You can't spin a 1 and be on 8 at the same time. Okay, so for example, consider one spin of the wheel, right? So I could spin 0 through 9, so there's 10 spaces there. Event A, 0, 1, 2, 3, 4, and B is 5 and 7. If event A occurs, then event B cannot occur, right? If you get 1, 2, 3, or 4, then obviously you did not get a 5 and a 7. They are mutually exclusive. They do not overlap at all. If events A and B are mutually exclusive, then the probability of A or B is the same as the probability of the union of A and B, which is the same as the probability of A plus the probability of B. I am not a big fan of unions and intersections and all those. They always just kind of bug me, but it is kind of important to know that if I give you an or, we're basically saying add the 2. Okay, the probability of the union event such that any 2 are mutually exclusive is the sum of the probabilities of those events. Okay, let's move on. So now, complementary events. So 2 mutually exclusive events, right? Remember, they have absolutely nothing in common, whose union is the sample space, are complementary, okay? So the sample space in our problem is 1, 2, 3, 4, 5, 6. Basically, think of it as a die. For example, consider the event 2 and 4 of tossing a 2 or 4 on a standard die. The complement then is 1, 3, 5, and 6, right? So if 2 and 4 are your event, then its complement is everything else, okay? Complement is everything else. If A is an event, A bar is its complement, okay? The complement is everything else not in the event. Okay, and when you put the two together, it equals 1. It will always equal 100%. Okay, the two together will always equal 1. Or if I give you 1 and say, hey, what's the probability of the other? You can always subtract it from 1. So if I'm like, hey, guys, I want the complement of A, right? You can always find it by taking 1 minus whatever that probability was. So going back a screen here, right? This is 2/6 or 1/3. Right? If I said, because I, had no idea what it was, and I'm like, what's the probability of the complement of A, right? 1 minus 1/3 would give me 2/3. And if you look, if I scroll back again, 4/6 is the same as 2/3, right? So those two things, you guys follow, are going to work together. So if I know one, I automatically can find the other by subtracting it from 1. Okay? Now, non-mutually exclusive events. In other words, now we're going to have something that has some kind of an overlap. You don't ever want to double count, okay? Don't double count this. All right, so take a look at our spinner here. We've got all these numbers on there. Let E be the event of spinning an even. So 2, 4, and 18 are the only evens that I have on there. Okay, and then let's say I have T be a different event, and it's the multiples of 7. So I'm like, okay, I want all the multiples of 7. So 7, 14, and 21. And in the process of doing that, you notice that I have an overlap. I have 14 circled and squared, right? So in this case now I'm talking about a union, and so I need to know the number of units. So me personally, this is a small enough set, I can easily find this by just going, okay, 2, 4, 18, 7, 14. Oh, it's an overlap. So I'm just going to not count it a second time. Don't count that double count, right? So I've got 1, 2, 3, 4, 5 of them. And how many are in my whole thing? 1, 2, 3, 4, 5, 6, 7, 8. My answer is going to be 5 out of 8. Okay? Don't count the overlap. So let's take a look at another couple examples here. Okay? A golf bag contains 2 red tees, 4 blue tees, and 5 white tees, right? To tee off. What's the probability of the event R that a tee drawn at random is red? So we want the probability of drawing a red. Well, first of all, how many tees are in the entire bag, right? I need to know the total. My total is 2 plus 4 plus 5, and that's what, 11. So I have 11 altogether. And how many of them are red? Red, I've got 2. 2 red. So the probability of getting a red is 2 out of 11. Can I reduce it? No, I'm good. What's the probability of event not R or not red? Okay, so this is the complement. I'm asking about the complement of red. Okay, so when I asked for the complement of red, well, what was red? Red was 2/11ths. So I want the probability of not R. So 1 minus 2/11ths. Now, my students would be all freaking out because they're like, oh, a whole number minus a fraction. Yes, but I can take my whole number and make it 11/11ths. 11/11ths is 1 minus 2/11ths, and I get 9/11ths are not red. And if you go back and actually look at the list, look at it. 4 blue, 5 white, 4 and 5 is 9 out of 11. Amazing. All right, let's try this next one. What is the probability of the event that a T drawn at random is either red or blue? Okay, what's the probability that it is red or blue? Okay, so how many of them are red? Well, we had what, 2? 2 out of the 11 were red, plus how many are blue? I gotta back up and look. 4. 4 of them are blue. So what's the probability of getting that? Well, they have a common denominator. That makes life easy. 6/11ths. Okay, so we have a 6/11th chance of getting a blue or a red, right? You don't care, you're just going in and grabbing. All right, let's take a look at what else we have. Alternative definition of probability of an event from a sample space with equally likely outcomes. Probability of the event is the number of favorable outcomes over the total number of outcomes. Okay, probability of it happening out of all the possible chances, right? Number of favorable outcomes is the number of it actually happening times it happens, or or times that you could possibly get it, and then the total number of outcomes is literally out of all possible outcomes. All right, now geometric probability. I am such a visual learner, so I really do like these, and I think with the younger grades, they do work really well. A probability model that uses geometric shapes is an area model. And when an area models are used to determine probabilities geometrically, outcomes are associated with points chosen at random in a geometric region that represents a sample space. This process is referred to finding geometric probabilities. So take a look at this one here. You could, instead of giving kids a coin, right, you could also model it by having them have a spinner and having heads and tails. Because, hey, my middle schoolers, coins get thrown across the room. You know, not that I have a disruptive room, but, you know, that is pretty common to have happen. Rolling a die, right? You don't have dice because, hey, you're a poor college kid just straight out of college and you know, are starting your job and you're like, oh, what do I do? You can actually make a spinner and you could have them spin, and now they've got a coin or a die. Okay, that is all. So what I need you guys to do is do the best you can with my lesson and reading out of the book to be able to get everything done that you need to for the homework. We got to stay caught up. So I'm probably going to do this for you guys, at least for this one, if not another if we have to. I will see you guys next time we have class.